Okay, good morning. Okay, let's try that again. Good morning. Much better, thank you. Okay, I brought up this test drive thing again. If you've never taken an exam in Elliott Hall, you want to check it out, see what it's like. If you think test anxiety is going to be an issue, find out, see how big an issue it is. So if you're interested, remember you have to register online at the web address at the bottom of that card there. And do it as soon as you can. Space is limited. Okay? And by the way, that thing is posted on the course webpage too, so you can go take a look at there. All right, so today we're going to be looking at section 2.6. On limits at infinity. And let's start with a very simple function. F of x is equal to 1 over x. Very simple function. And if you're looking for the limit as x approaches some a, whatever a is equal to, we know what to do. If a is just a regular number, 3, 4, 10, even 0, we know how to handle this kind of thing. And now we're going to look at what happens if we push this number to a very, very big number, to infinity, or a very, very big negative number to negative infinity. And what you do here is slightly different because infinity is not a number that we can handle, like 3, for example. It's a very large number that is not fixed. It gets bigger and bigger and bigger. Same thing with negative infinity. So let's check out what happens if we progressively make this number bigger and bigger. We want to push x to become a very large number and keep pushing it to be even larger. And we'll notice what's going to happen to 1 over x. So this is a very simple exercise. We just want to see the trend that's going to fall out of it. Okay, let's start with 1,000 maybe. It's pretty big. 1 over x is 1 over 1,000, so that's 0.001. Tiny number. Let's make this 1,000 times bigger. 1 million. F of x is 1 over that. 1 over a million is 0.000001. So 1,000 times smaller. A tiny, tiny number. Let's go a couple more. How about 10 to the 9th? 10 followed by 9 zeros. 1 over that would be 0 point, bunch of zeros, right? In scientific notation, it's simply 10 to the minus 9. And 10 to the 12 gives you 10 to the negative 12. Okay, so these numbers get progressively smaller when I make x larger and larger. As x becomes a large number, think of infinity as a large number, very large number. We see that 1 over x approaches a very small number, becomes a very small number. Right? So how would you express as a limit what 1 over x is going to go to? Negative infinity? 0, yeah, exactly. These numbers are always positive, but getting smaller and smaller. Now, if I keep pushing that, this will get even smaller. Eventually, it will become so small that it is practically 0. Never exactly equal to 0, but practically 0. So we say, in this case, we would say the limit as x approaches infinity of the function 1 over x is equal to 0. Remember, when you talk about limits, these things are never exactly achieved. Even if the function could get there, but that's irrelevant. The way you want to read this is x is a large number. And the way you want to interpret that 0 is a very small number. Never exactly 0, but eventually practically 0. In fact, if you put this in your calculator, it gets to the point that eventually your calculator is just going to say 0, even though it's not exactly 0. It becomes so small that the level of precision of your calculator cannot provide that number. All right, so knowing what we just found out, what do you think the limit of that would be if we push x to a very large negative number, negative infinity? What do you think? Still 0, right? The difference is that the bottom row of numbers would be negative, but they get progressively smaller. They actually get closer and closer to 0 from the left side. So yeah, absolutely, this would also be a 0. What about 3 over x? What do you think? Still 0, right? Because downstairs still gets really large. Upstairs is 3 times bigger, but downstairs is getting so much larger. Eventually, this will get to a 0. Think of it this way. Think of it as the limit of the number 3 times 1 over x. 3 doesn't care what x is doing, but we know the limit of 1 over x as x goes to infinity is 0. So this is 3 times 0, eventually goes to approximately 0. And there's nothing special about that 3, right? Any number, any constant number I put here, this will still go to 0. So limit as x approaches plus or minus infinity of any number that's called as c over x is equal to 0. C could be positive or negative, fractional, any real number. This will eventually go to 0. Because the denominator grows without bound, while the numerator is bounded at one number. What if I raise the power to 2 for x? What changes? What's that? Yeah, exactly. The denominator still become very big. In fact, gets a lot bigger faster. So the overall ratio gets smaller faster. Okay? So x goes to plus or minus infinity of any constant number over x to the n goes to 0. The only thing that's going to change is how fast the denominator grows, and therefore how fast the overall ratio goes to 0. As long as n, this number n here, is greater than or equal to 1. The higher n is, the faster the denominator grows. And therefore, the faster c over xn decreases. Actually, I'm sorry, it shouldn't be 1 here. Let's make this like 0, right? We can't have a negative n. What happens if n is negative? They would go to infinity or negative infinity, right? If n is negative, then a negative power downstairs means a positive power upstairs. So c over x to the minus 2 is c times x squared. Now, if x is going to infinity, then that thing's going to blow up. So this is only going to go to 0 if that n is a positive number. Okay, now, as long as you know these two, actually this one right here, any more complicated stuff can be handled just by using this little building block right here. Okay, so let's check out this example. Let's look at what happens when x becomes a very large number to the rational function 4x squared minus x plus 1 over 3x plus 5x minus 3. Okay, so first we're going to go through using what we just saw. C over x to the n goes to 0. And then after a few examples, we're going to notice a pattern. And that's going to allow us to find out these limits pretty quickly. So first, let's just make use of what we just saw. So I would like to see a bunch of c over x to the n in this expression right here. The best way, the easiest way to do that is to divide the top and the bottom by x to the highest power. In the denominator. This is one of the easiest way to introduce a bunch of these into that whole expression. You could also do long division if you want to, but that's a more lengthy process. It's easier to do it this way. All right, so I notice the highest power is a 2. And I'm going to divide the top and the bottom by x squared. You can always divide and multiply by the same thing. This doesn't change the function at all. It's still the same thing. I divide it by a 1, essentially, or multiply by a 1. Okay, so you look for the highest power, 2 here. We divide it up and down by x to the same power. Okay, next step, let's break things up a little bit. Look at the numerator here. We got a bunch of things added to and subtracted from each other, all dividing by the same thing. This is equivalent to individual terms dividing by x squared. So this is 4x squared over x squared minus x over x squared plus 1 over x squared. Okay? Anytime you got stuff added to or subtracted from each other, dividing by the common thing, all of these things get divided by the same common thing. Same thing downstairs, 3x squared over x squared plus 5x over x squared minus 3 over x squared. Simplify a little bit. This is a 4. That's a 1 over x. That's a 1 over x squared, doesn't do anything. That's a 3. That's a 5 over x minus 3 over x squared. Okay, and so you see what you got here. You got a bunch of this going on here. The 4 doesn't care what x is doing. But this is a number over an ever-growing denominator. This goes to a 0, right? So that goes to a 0. I'm going to write it this way. This also goes to a 0 for the same reason. The denominator is always growing. The numerator is bounded. Same thing here. This goes to 0. That goes to a 0. And the only thing that's left here is the number 4 and 3. Those don't care what x is doing. So the limit overall is going to be 4 over 3. All right? Does that make sense? Any question? Okay, now let's check out what happens if we let the limit go to negative infinity. In fact, nothing changes. Nothing changes whatsoever. You still do exactly the same thing. You make a note of the highest power in the denominator, divide the top and bottom by the same thing, just like what we just did. As far as what we do, nothing changes. Everything is exactly the same. Four x squared minus x plus 1 over x squared. 3x squared plus 5x minus 3 all over x squared. Exactly the same thing. 4x squared over x squared is 4 minus x over x squared plus 1 over x squared. 3x squared over x squared plus 5x over x squared minus 3 over x squared. And now x goes to a negative large number, minus 10 trillion, for example. This ratio here is still going to be a very, very small number, practically 0, right? So that guy still goes to 0. 1 over 10 trillion squared, that is practically 0. Not exactly, but practically. 5 over 10, negative 10 trillion squared is still 0, roughly. Minus 3 over x squared, 3 over negative 10 trillion squared, that is still roughly 0. So what you do, whether this goes to infinity or negative infinity, doesn't change. The process is exactly the same. And we still get a 4 over 3. Most functions that we deal with will have the same limit to positive and negative infinity. Or rather many, I'll say many. Many functions have the same limit at infinity and negative infinity. For rational functions, that's almost always true. You will encounter some exceptions. We'll see examples later. Two very prominent exceptions are things containing root, square root, cube root, that kind of thing, and exponentials, e to the x, 2 to the x, that kind of thing. Again, we'll see examples in a little bit. But for now, it's useful to remember that almost all the functions you will encounter, most of the time, will have the same limit to infinity and negative infinity. But when you see a root somewhere in the expression or exponential somewhere in the expression, you've got to be really careful. Okay, so let's think about what these things tell us about the graph. Okay, this is saying that if I push x to be a very, very large number, I get a certain limit. If I push x to be a very, very small number, I get a certain number. This is saying that the larger you make this x's, the closer that function approaches this number. The larger negative number you make x, the closer this thing will get to that. Okay? It doesn't quite get there, but gets awfully close to it. And in fact, the more you push it, the closer it gets to. And so what this is telling us in terms of the graph is where the horizontal asymptotes are. That's what horizontal asymptotes do. Asymptotes attract the graph of the function. The bigger you make x's, the farther you push to the right of the graph, the closer y is going to get to that number. So that's just like exactly an asymptote. Negative infinity is when you push it to the left. On the right, when x is a large number. And negative infinity, of course, is the left side. That's horizontal asymptote on the left. Okay, so the example we just did, we found out that the limit of that function, whether we go to infinity or negative infinity, turned out to be 4 over 3. So what that's telling you is that the graph is going to get closer and closer to the horizontal line. Y is equal to 4 over 3. The farther you push it to the right or to the left side. It doesn't tell us anything about the region near the origin, but it tells us the behavior as we push things away. Okay, so we don't know what's going on in the middle. We can graph it if we want to, but the limits don't tell us anything about what's going on in the middle, but tells us the tail ends on either tail. So we expect the graph, as we push x larger and larger, to be getting closer and closer to 4 over 3. So let me draw a rough sketch. It does this kind of thing. Now, what's going on in this region in the middle? We don't know from the limit, but we don't really care if you just want to find out the behavior of that. On the left here, the closer and closer you push this to negative infinity, the function still gets closer and closer to 4 over 3. It actually turns out to be something kind of like that. We get no information about the middle part, but we get a lot of information about the boundaries of that graph. Does that make sense? Questions? Okay, let's look at a couple more. All right, so same thing here. We have a rational function. We want x to go to infinity or negative infinity. For most cases, remember, it doesn't make a difference where we go. I don't see a root. I don't see exponential. So I know the limits will be the same on the right and to the left. And we do exactly the same thing as we did before. The highest power downstairs is 2. So I will divide by x squared up and down. Okay, so what do we see? We see limit x goes to infinity. Same thing as before. Things added and subtracted to each other, divided by the common thing. So divide things one at a time. X over x squared is 1 over x minus 7 over x squared. Downstairs, x squared over x squared, that's a 1, plus 9 over x squared. Okay, so what do we get? 0, yeah, exactly. Both things upstairs go to 0 because the denominator is growing very, very large while the numerator is bounded. Downstairs, 1 doesn't care. This goes to a 0. So we get a 0 over 1 plus 0. Therefore, that's a 0. Okay, now a slightly faster way to do these things. X goes to infinity means x is a very large number. Large number. Think of a very, very large number, 10 trillion. 10 trillion, okay? What's 10 trillion minus 7? Roughly 10 trillion, right? Yeah, exactly. So 10 trillion minus 7 is still roughly 10 trillion. That minus 7 really is irrelevant as in the big picture here. Okay, what's 10 trillion squared plus 9? Roughly 10 trillion squared, right? That plus 9 really makes no difference. When the number is so large, adding and subtracting numbers to them really makes no difference. So that means that the ratio of x minus 7 over x squared plus 9 is roughly x over x squared, right? Which is roughly 1 over x squared. 1 over x, sorry. So this tells us the limit as x goes to infinity. You know, we don't stop at 10 trillion. We go to 100 trillion, whatever you call 1 trillion is. You don't stop. You keep pushing it. So now we see that this whole thing eventually behaves just like 1 over x. So it's the classic case of a number over a large number. That goes to a 0. Look at the previous example, this one right here. You can use the same reasoning. If x is 10 trillion, 4 times 10 trillion squared minus 10 trillion plus 1, this is still going to be far larger than these guys. Far, far larger. So when x is very big, these things, other than the highest powers, don't really matter. They are irrelevant in the big picture. So overall, we get a 4 over 3. Okay. Let's flip that ratio, that rational function around, upside down. And now we can very quickly find this limit, right? As x goes to infinity, 10 trillion, x squared plus 9 is roughly x squared. Then plus 9 makes no difference. X minus 7 is roughly x. That minus 7 makes no difference. Subtracting 7 from 10 trillion is still roughly 10 trillion. So therefore, the limit of this thing here is going to behave just like the limit of x squared over x. Once again, these numbers added and subtracted to super large numbers don't make a difference. And that eventually is going to behave just like x. So what this is telling you is that the graph of this thing here is complicated, but when x becomes large, the behavior of this graph is going to be very, very close to the behavior of x. when x is a very large number or very large negative number, that is going to behave just like that. Not equal, but just like it. Essentially the same. So here we see that x goes to infinity, x of course goes to infinity. Okay, so we can actually draw some pretty useful conclusions here. For the cases we just looked at, we have a polynomial over another polynomial. Look at the most recent example we did. Notice that if the power upstairs, the highest power upstairs is higher than the highest power downstairs, then upstairs will grow faster than the denominator. Eventually, it will overwhelm downstairs, and therefore, the limit goes to infinity or negative infinity. Okay, so let me write that down. If f of x has higher degree, like the one we just saw. Higher degree is the highest power in that polynomial. If f of x has higher degree than g of x, of course, then the limit is either infinity or negative infinity, depending on the sign of that ratio. It'll go to a very large number or a negative number, large negative number. If my overall ratio is negative, then eventually it'll push to negative infinity. If the denominator has higher degree, so that's the example before that, x minus 7 over x squared plus 9, right? Eventually, the denominator will dominate what's going on up there. And the limit eventually will go to a 0. If they have the same degree, like the first example we did, what do you notice? If they have the same degree, what do you notice? The ratio of the coefficients of what? The highest power. Yeah, exactly. So you can again reason the same way we did. When x is very large, negative or positive number, these two are the dominant terms. So eventually everything don't matter anymore. And look at them. If they have the same degree, then the ratio of the coefficients will end up being the limit. And I'll write that down. If f of x and g of x have the same degree, the limit is the ratio of the coefficients, the number in front, of what's called the leading terms. Leading terms are the terms with the highest power. They are not necessarily always arranged in a way that it shows up first, right? You can arrange these things any way you want, but leading terms, by the definition of leading term is the one that has the highest power. So just like the example we did first, when they have the same degree, take the highest power terms, look at the coefficients. 4 over 3 is the example we saw earlier. Okay, do these make sense? Yes? Okay, good. All right, now when you encounter root, stuff with root, remember, things are a little bit different. Actually, let's first look at an exponential case. Let's say f of x is 1 minus e to the x over 1 plus e to the x. This is one of those functions that the limits to either side will be different. Whenever you have exponential or root, which we'll see next, you can have these different behaviors on the right and the left. Let's check out the one going to infinity first. When x is a very large number, 10 trillion again, I like that number, 10 trillion. What's e to the 10 trillion? Very large number. What's 1 minus that super large number? Roughly that super large number, exactly. Right? That 1 really is irrelevant because e to the 10 trillion is so large. Downstairs, 1 plus e to the x, for the same reason, is roughly e to the x. You add 1 to e to the 10 trillion, it's essentially e to the 10 trillion. That thing is so much larger than 1, it completely dominates it. So this limit right here is going to be the same as if those 1s were not there in the first place. Make sense? And what's this going to? 1, right? Negative 1, sorry. Negative 1. Okay, well that's easy. Let's try the one going to negative infinity. All right, so what's e to a very, very large negative number? What's that? A very tiny number, exactly. If e is a very large, let's say, for example, let's say x is minus 1 million, or that one doesn't matter, one super large number. Now, e to the negative that thing is equal to 1 over e to the positive that thing, right? Too many zeros? 1, 2, okay. Oh, you get the idea. It's a large number, right? So this is a very, very tiny number. Okay, so what's 1 minus e to the x roughly equal to? 1, yeah. What's 1 plus e to the x roughly equal to? 1, absolutely. Yeah. So the limit right here is going to be 1. So we have a y equal to minus 1 as the horizontal asymptote to the right, and y equal to 1 as the horizontal asymptote to the left. Okay, the last example I will do, this is a tricky one here. It's a one with root, and it's not in the form of a fraction. These are the trickiest. So if you look at what's going on here, when x is very, very large, this is obviously very, very large. This is obviously very, very large too. So this approaches this funny looking thing here, infinity minus infinity. Now here you're just going to be really careful that you can't treat infinity like a number. Infinity stands for a large number. We use the same symbol for all large numbers. There's no way in knowing, just by looking at this right here, which of the two is larger. This could be 10 trillion, this could be 100 trillion, or the other way around. Or this could be 1 trillion and 1, this could be 1 trillion. The important thing to take out here is that we don't know what that is. We don't know which one is larger. And more importantly, by how much. And there's no fraction here. We can't do the trick we've been doing to find the limit. So with these kind of things, what we're going to do right here is to rewrite it this way. And we'll do the same old trick we've been doing whenever we encounter difficult radical stuff. We rationalize stuff. So I'm going to rationalize that expression this way. This is a good trick to keep in mind. Whenever you see root things and you don't know what to do, consider rationalizing. Rationalizing, right? All right, so now look at this on the top here. When you multiply these things out, you get this thing squared. Minus 16x squared. Downstairs, I'm not going to do anything to it. Now, what's nice about the numerator is that these 16x squares go away. We just have an x. Okay? And now we can do the same trick we've been doing here. 16x squared plus x, when x is very large, that is going to dominate. So that is approximately 16x squared, right? So radical this thing right here is roughly radical 16x squared, which is roughly 4x. Same trick we've been playing all this time. When things become large, only the leading term, the term with the highest power, truly matters. So in the end, notice that this limit is going to turn out to be, this guy is basically 4x. So what do we get? We get 1 over 8. Okay? So these are the tricky things. Again, keep in mind that you get root stuff, you really don't have any idea what to do. Rationalize the thing. You might get somewhere. If not, then think of something else. All right, have a good weekend. See you Monday.
Yesterday.
Yesterday, yeah. Yesterday evening. So,